Hello everyone, am I audible? Let me know. Let me just check out as well. Okay, seems perfect. Uh, let's get started, guys. Today we'll be talking about yet another topics from machine learning, and in which I'll be talking about selectively SVM, perceptron, and neural network. Basically, multi-layer perceptron. I'm talking about. So I'll be solving questions on that, and we have things lined up. So we'll get started with that. Now, if you can recall from the last session, we had the one guidance part which was remaining because of the overtime we had. So I'll be talking about that thing first, and then we'll get started with our topic of the day. Okay. So let me just bring it up as well, just for the purpose of understanding, for your understanding, what we are having today. Yeah, we have a lot of things today. Wait. So like this, today we are having SVM, perceptron, and MLP as we talked about. And I also mentioned that we'll be talking about something important over here, a non-technical thing, which is how shall you be attempting the test series regarding that. And then we have all the things lined up, which we generally have always, and a number of problems. Today we are having interesting set of questions. I hope you'll be enjoying those. Okay, so let's get started for the first part, which is the motivation session. Not exactly motivation, but guidance session right now. So, how do you generally attempt test series is different from how you shall be, and if you are really aligned with what I'll be telling you, in that case, you're already doing good. Okay. So, with respect to the test series, so I'll just take like 10 minutes max, and then we'll get to our point of discussion, which is the set of problems and the cheat sheet what we are having. Okay. So if I talk about the test series, you should always make sure that you're going in a cyclic method. What do I mean by that? So for any question you will be watching out, or you'll be having a look at within your test, give yourself 10 to 15 seconds, maximum 10 to 15 seconds, I'm saying, to decide after reading the question, to decide whether you can solve this question or not. If you are like, oh, I'm damn confident I can solve, you should solve it then and there. If you're not confident, even 1% of doubt you're having, then skip that question, move on to the next, and repetitively do this thing with each and every question. Now, how does this thing help? First thing, it will save you time. You'll not be wasting your time on the questions which might decrease your confidence, and you'll be building your confidence by solving those which are really like easy questions for you, or where you are really confident. So there are two things: your confidence is not decreasing and your confidence is increasing only. Okay. The other third advantage is you're saving a lot of time over here. Okay. Now this is, so you'll be going from 1 to 65 like this, and 1 to 65 question, and by the time you reach 65, I guess you'll be done within like easily 1 hour, if you're going by like this now, because you'll be skipping a lot of questions. Even for a topper, maximum chance they'll be skipping a lot of questions in the first round. Okay, because the moment I said 10 to 15 seconds you shall be waiting maximum after reading is the idea, so that you just build up your confidence, do not decrease it while getting stumbled upon some difficult question, okay, or something which you were not comfortable with. Once you're done with that, now you'll again start going through the loop. That means from 1 to 65 again you'll go. But right now you already have an idea what were the kind of questions you had. You must have marked some of the questions. I feel I can solve these questions, but not right now within the first iteration. So you'll be going to those questions in the second iteration. solving those which you feel you can solve, but it might take time, or the question was too much lengthy. Okay, so if the question is also too much lengthy, in that case also you shall skip those questions. Okay, I hope that idea is particularly clear over here now. Now, what is the next thing? You solve those questions in the first go where you're confident, you knew it. Second round was you thought that either the question is too long to read, or the question was in such a way such that you were a little less confident, so you are giving it some time right now to solve. Now the moment you will be finishing up with this particular thing, because you'll be writing in your notes, like not exactly notes, on your what should I say, like your a rough notebook kind of a thing, a pad you'll be getting. Okay, so on that you'll be writing down everything while solving that question. Make sure to write neat and clean. Okay, if you feel you are going to get answer very soon, so for an example, if I'm saying you should get solution is, I'm saying maximum 5 minutes. Maximum 5 minutes you shall be taking for the question you are having. Maximum 5 minutes. Okay. In the second iteration, because you are already giving it good enough time, reading and then solving. And trust me, easily questions can be solved within 2 to 3 minutes. Okay. If you are really confident about those questions. But if that is not the case, in that case, please be mindful of you should not be taking more than 5 minutes, or you shall have some idea. Not if not 5 minutes, like I can extend it to 7 to 10 minutes at max only, and then just skip those questions. Once you have that idea that you are going to skip those questions, now you are very much clear that okay, what do I need to solve? Okay, you again would be completing your second iteration, and you have some rough work done, some more set of questions done. So for an example, within first iteration itself, you solved around 30 question or maybe 20 question possible. In the second iteration, you'll be solving more and a little faster, because from the first iteration you got some confidence, okay, while solving some questions. So in the second iteration, again you'll be solving more questions. So by the second iteration, you'll be able to solve around 40 question easily. 40 to, like I can say 40 to 50 question if you are really thorough with your syllabus. 40 to 50 question you'll be able to solve. Now in the third cycle is something where you have those set of questions which are either you are not able to recall their concept properly, or you are actually doubting what you have done, or they were taking too much of the time. It was too long to solve. So in that case, now your work, your time would be properly optimized for those set of questions which were a little heavier for you. Now, why this approach is better as compared to the normal one where you just keep on solving? You might give away a lot of time to a particular question, ignoring those easier questions which must have gotten you more marks in less time. Okay, so you have to be very careful about time optimization and management as well. So that's the reason a cyclic method I have told you. Now, just last 2 minutes I'll be talking about further into this, maximum 2 minutes. Now, after you are done with the test series, so like not the test series, make sure you write down everything in your personal notebook, which is with respect to the test series only, where what were the silly mistakes you made. Write those down, very important for you. Okay, write down those things apart from like silly mistakes where you felt you could have solved it in lesser time, but you took more time, because that will help you optimize your time for those kind of questions. Because it would always be happening, sometimes you might get some tricky question, some new question, so those would be taking initially good enough time. So you have to optimize your time over there. You have the knowledge to solve them because you solved it, but the idea is to optimize the time in those questions. And for those questions where you did silly mistakes, understand why was it so, what were the mistakes you were making, what was the gap in your knowledge you were having. And after that, lastly, if you could not solve any questions, be mindful of you have limited time, because I have been saying this, just 2 months of time nearly. And within that, if that particular question which you could not solve is belonging to the topic which was basically you have left it, in that case, depending upon do you really want to give it that particular topic a try or not, you should learn that topic, or you can leave it as well, depending upon what is the kind of question that particular question is. Sorry, what is the quality of that question is, or what is the type of question that is. For an example, if it's an easier question, you should definitely, learn from that question or from the concept which you have not revised or which you have not really covered yet. If it's an easy question, if it's difficult, leave it, because your target in test or gate exam would not be most of the time to score 100 out of 100, but would be to maximize your marks. And if it goes to 100, it's good. Okay, so maximize your marks. That doesn't mean you need to score or you have to score 100. Even if you're getting 80, 90, just think about this. How many people get 90 plus? How many people get 80 plus? So you can think of this. Like 10 marks getting deducted, 20 marks getting deducted is still fine. You'll still be in top 100. So what does that mean? You need to optimize your time, your understanding, your learning in such a way such that you get maximum possible gain. And you can leave a number of questions or topic as well, depending upon how much time you have. Okay, so that was all about how to attempt your test series. Now we'll get into the idea of what we have planned today, which is going to be our topics of the day, which I talked about. That is your SVM, perceptron, and MLP. So we will be solving questions on these 3 topics today, 20 questions. I hope you'll love it. Okay. So before solving, let's go through the cheat sheet we are having. So in SVM, we generally have 2 formulations. One is hard SVM, one is soft SVM. Hard SVM does not allow any misclassification. Okay. And then this is our objective function we are having with some constraint. You can see over here. Then there is a distance. Now, when we talk about distance, there are 2 types of distances available. One is margin, which is called distance from the hyperplane to the closest point. Okay, that means the support vector point and the and the hyperplane. That is 1 by mod of W. The total margin width is like both the sides. If you can recall the diagram, we have a number of questions on that. Okay. Now, what is the decision function? It is going to be your sine of W transpose X plus B or W dot X plus B. Okay. The geometric intuition, we always look for maximizing the margin. The pros, if I talk about, it is strong margin based. So basically geometry based approach over here we are having. The cons is if the data points are not linearly separable, in that case we have a problem, and it is extremely sensitive to outlier if they are very close to each other. Okay, so very sensitive to the outliers. Similarly, we have the soft margin SVM, in which case we allow some misclassification, okay, or we allow our data points to cross the margin lines as well. Okay, so there we introduce the slack variable, which basically captures the kind of penalty I'm having, or basically the violations I'm having. And then in that case, this is my objective function, C times my slack variable. Slack variable is just telling me how many misclassification or how many times my data points are crossing my margins. And C is just a regularization kind of a parameter over here, which would determine the strength of whether you like how much of misclassification you can allow or you don't want. Okay, any misclassification. So role of C is already written. If C is very large, in that case we have a hard margin, like hard margin problem. In case a small C is there, in that case what we are saying is I can like maximize my margin. I would still be fine with any kind of misclassification. Not any kind of, but a number of misclassification are fine with me. So it just depends how much I can allow. Okay, depending upon the value of C. Okay, we have this hinge loss within SVM, and then we have the kernelized decision function. We use the kernels as well. Need not worry about the kernels. Very less chances for a question to be asked on the kernel. So I have not kept any question on kernel over here, but still, just to give you the idea, like kernel is a kind of just extra calculation being done on your features only. Okay. Pros, if I talk about, so yeah, it works for the non-perfectly separable data as well, robust to outliers, because we can just tune it for that. Okay. So it's C is a regularization parameter, which we need to handle. And if we really want to go for the non-linear decision boundaries, in that case, we can just use kernels or like advanced feature engineering kind of a thing. Here are the short points over here. SVM naturally handles, so like you can just read it through. Very simple thing over here right now. If I talk about the perceptron, again, it's very simple. It just works upon the sine of W transpose X plus B Okay, so like the activation function over here, most of the time what we consider is the sign function only, telling me what shall be the sign of my W transpose X plus B. Okay, now if I talk about the formulas, that's what we have already talked about. There is an update rule which actually applies only in case of we had any misclassification. Whenever what we predicted and what we have actually are mismatching, in that case only we have the update rule applied. And how do we apply? So there is a different rule as well, different equation for this as well, which I have kept in the question, which will discuss how they are different or similar to each other. Okay, and that's like similar to something like gradient descent. I'm saying similar, not exactly same. Okay, so we have that, and eta over here is nothing but similar to your kind of learning rate. Okay, so points you can see again very important over here. The next we go for MLP, multi-layer perceptron and feed-forward networks, and the sigma over here is just telling you the activation function on at each layer what you're having. And if I say L minus 1, what does it represent? What was the input I was getting from the previous layer? Okay, and this is going to be the output of the current layer. So that's how it actually works. Simple common example over here, we will be having a number of perceptrons over here, and that's how we will be working to create hidden layers and a number of hidden layers on top of just one simple input or output thing. And that's how we basically build our multi-layer perceptron, or basically the basics of neural network. Okay, now the back propagation, it's very important. See, back propagation is not really in the syllabus, but this is something which actually solves a number of things with respect to your neural network or MLP. So that's how it becomes important. So people keep on asking this thing, that sir, this particular topic is not mentioned in the syllabus, then why? Like last year, this is what happened. Some of my students asked, like when I gave this question, I asked this question, that why are you asking these questions? So it's very important that it is one of the main component which actually leads to the working of our neural networks or MLP. So we should understand that. And we have some questions. And there was this question asked in 2025 exam as well on this back propagation idea. Okay, so it's a simple thing. Gradient descent you should know, and you should know the chain rule, and then the work is done. We have a question which we'll be solving, which will help you understand this concept. Okay, then there is a very important a theorem, what I shall say, universal approximator. So neural networks are basically, they can approximate any continuous function given the sufficient layer size. So if you have like what we're talking about, the depth and the length as well of our neural networks, in that case, if we have a number of nodes within layer, and if I arrange a number of hidden layers, in that case we can really approximate any continuous function. Key points, you can just check it out, very important, but still like just small things which you need to take care of. So now is the time of questions, and I guess you had been waiting for this particular thing. Let's get started. We'll be solving the questions from now. Okay, so this is the first question we are having. Let me share my screen as well. Okay, you can just try. Until then, I'm just loading my screen for problem solving. Okay. Cool, guys. I hope you can see my screen right now. So let's get started. So where were we? You were solving our first question. Yeah. So for the sigmoid activation function and the ReLU activation function, which of the following are true in general? So what do you think is the correct answer over here? I hope you have gone through the question and you must have thought for your idea what exactly should be the answer over here. Now, if I just talk about So ReLU is a, like, just to share this, like how do they actually look? Okay, we shall be having that idea as well, that how do they generally look. So if I talk about our ReLU, so that is simply max of 0 comma value what we are having. So in that case, it actually behaves like this. So if I want to draw it, this is how it looks. Okay, and if I talk about the sigmoid function, how does it look like in that case? It's something like this. Sorry, 0 to 1. It is, my bad. If it's 0.5, oh, this is yellow is not visible. If it's 0.5, then in that case, and this is 1, this is how it looks like. Okay, a generally kind of S shape, but sorry for my bad drawing over here. It generally is like this only. So you can see it is non-decreasing, monotonically non-decreasing. Both the functions are monotonically non-decreasing. So yeah, A is true. What about the derivative? Are they? So you can just check out. So this is not really the derivable, but because of at 0, but still you can just check it out, that do they have their first derivative monotonic? That means like either increasing or decreasing or non-decreasing or non-increasing only. So answer you'll get is no. Just check it out, solve it, you'll get it. Okay. Compared to the sigmoid, ReLU is more computationally expensive. Is it? No. This is ReLU, very simple. And if I talk about sigmoid, that is something like this, 1 upon e to the power minus x. So you can see over here, this is a little more complicated because it involves exponential function. Okay. So this is again false. What about this? Sigmoid derivative is quadratic in S. So if this is my S of x, I hope you understand that S dash x, this is one of the exercises we do in the generally in the class. What you will get is it is 1 minus S of x only. Is it 1 minus Sx? Sigmoid, yeah, sorry, 1 minus Sx into Sx. This is what you get. And in that case, if you're comfortable with it, what you are getting is actually nothing but Sx minus Sx square. So it's a kind of quadratic function within this, in terms of this function itself. So yeah, that is quadratic. So A and D are the correct option over here. I hope you could understand. Okay. If you have any doubt, you can just write in the chat. If not, let's go to the next question. I hope we are doing good. Let's move on to the next question. This is something interesting. I guess we can't really see it in the entire screen. Yeah, I guess this is visible. So let me just keep it like this. Okay. So we have this question, which I'll be basically asking you something which is very relevant with your back propagation, the way we actually calculate the back propagation. But need not worry, the diagram seems to be complicated, but it is very simple. Need not worry, we'll talk about this. Okay. So consider the cut section of a deep neural network as shown in the diagram given below. It can be seen that it has two inputs, x1 and x2. Yeah, we can see that. And this is for the bias term. Okay. So Z, what is Z? Z, what you'll be getting is, this is adding after multiplying with the weights, and then you're getting Z. So this is your Z function. Now, you are doing something over here. From Z, you are getting Z1. And what is that? You're multiplying it with -1. So yeah, that's what we are doing over here. I hope you can see. Now, what's next? Within that, what you're having is, you're taking exponential of Z1. Okay. So Z2 you're getting is by taking exponential of this. How you're getting Z3 now? Z3 is after adding +1 to it, you're getting Z3. Now what's next? You're taking 1 by of Z3, and then you're getting the final value over here, which is your function f. I hope you can see that. Okay, so this one. Now if you look at this carefully, this block is nothing but your sigmoid function, as already mentioned as well. So you can just replace by something like this. You had z, then you can just write your function over here. Okay, this is your function, and then you are getting, let's suppose, whatever is the output, final output you are getting. And what is this f? F is nothing but 1 upon 1 plus e to the power minus z, because you first negated this z, then you took the exponential over here, negated, took the exponential, added +1 to it, and then reciprocal of it. So that's what you're having, sigmoid function only. This is nothing but your sigmoid function only. So now we are understanding that what we are having at f only over here. Cool. Now you are giving the value of inputs, x1 and x2 is given to you. This is 1, this is 2. Okay, the forward pass calculation. So we have all the values given to us. So that means z is given to be 1. You can see this vector. This is representing all these value. What is z1 value? Z1 value is -1. We understand by this thing only. This is nothing but 0.3679, which we understand. Okay. Okay. 1.3679. What is it? Okay, so this was this one, this was this was this, and then what are we having over here is 0.7311. Okay, so this was sigmoid and all, which is given to us. Over here it is concluded. We have this entirely. So we know J was our error. J was our error, and we already know, see, whatever is our error term, what do we do for updating our weights? We calculate what is the derivative of error with respect to the weights. That's what we try to calculate. And if you remember from the simple gradient descent algorithm, we update our weights based on these gradients values. Okay, so in that case, we are already having del j by del f is already known to me, which is 1 over here. Now what do I need? I needed to calculate del j by del z. We want what is del j by del z. If I get to know that, our work is done. So is it complicated? I know what is del j by del z, that is 1. I know what is my del f by del z. Do we know that? Yes, because we already know that my f is this function, and we just talked about that how do we calculate our del f by del z, or basically what is the derivative of sigmoid function. We know this, that if this is my f, my derivative would be nothing but 1 minus f into f. That is the derivative. Okay, so you just need to know what was the value of f over here. So we are having this, and we just need to multiply these two to get del j by del z. So we already have a space. So that means to calculate del j by del z, what we need to have is del j by del f into del f by del z. As I mentioned, this is what we are already having. This is 1. What is del f by del z? We know this is going to be 1 minus f by into f. Now, what is f value? What was the function f value? So I hope you remember we had it. F is equal to 0.7311. So just put it 1 into 0.7311 into, you subtract it from 1. What you'll be getting is 9851. Just multiply, and that is going to be your final answer. I hope you're getting it. Okay, I hope this is clear. I hope you're getting. Okay, so you just need to multiply, and then you'll be having an answer for this one. Cool. In case of any doubt, please let me know, and then we'll proceed to the next question. Again, very interesting set of problems we have today, because all the topics are very interesting. Neural networks, SVM. Okay, so I guess we are good. We shall proceed further for the next question. Again, a simple one. You just need to think about this. I'll give you just 1 minute time, or maybe less than that. Think about this, and then you will be able to tell me. See, you need to understand in neural networks, like if you can understand this, you are already like going to master deep learning very fast. If you can understand these concepts, because right now we are playing with the scalars. For proper architectures, we generally play with the vectors over there, but the concept remains a similar one. So in that case, you must be comfortable with vector or linear algebra or vector calculus. Okay. Apart from that, it's very simple and same. Okay. So what we are having is, again, we have a neural network kind of a thing. You can see the neurons are present. We have -2, -5. What is Q doing? Q is nothing but addition of these two. We had a Z value as well, which was -4. And what we are doing, Q into Z. And then we are getting F. So we need to know what is the gradient of F with respect to X, Y, and Z. So that means what we need to calculate, del F by del X, del F by del Y, and del F by del Z. Can we calculate all these? See, del F by del Z is very direct. Why? Because I'm calculating with respect to this. So whatever is the other variable, that would be kept as constant. So del F by del Z would be simply Q. Okay. Now I don't know how to calculate this one. Like del F is not in terms of X or Y directly. So how to get that? I know F is in terms of Q and Q was in terms of X and Y. So what do I need to do? Del F by del Q we need to calculate, which is going to be Z. And then we need to calculate what is del Q by del X, del Q by del Y. So what is that? Del Q by del X is 1. And what is del Q by del Y? That is also 1. I hope you can see that very easily. Okay. Now you just need to calculate all the values. So del F by del Z was very direct. How do you get this? Gradient with respect to Z. So this is Q. What was the value of Q? -2 and plus. It was an addition. So we had 10 over here. So Q value was 10. So it is 10. Sorry, 5 minus 2. My bad. I was just multiplying. Plus 5 minus 2 is 3. So what we'll be getting is 3 over here. Okay. Now what is del X by del Y? Sorry, del F by del X. For del F by del X, what we need to do is del F by del Q into del Q by del X. What is this one? This was Z into 1. What is the value of Z? So Z is -4. We already know. So it is going to be -4. And I guess for both the things, I'll be getting same because del Q by del X and del Q by del Y is 1. Same thing. And del F by del Q is Z. So every time we'll be having is Z into 1, Z into 1. So it's -4, -4, and 3. C is the correct option. I hope you can see. I hope you could get this. Interesting problem, good problem, simple problem, but still for better understanding, how do we do it? How do we all this? Okay. Cool. Let's move ahead with the next one. Again, a similar kind of a question. Making sure that you understand how does all this thing work. I'll just... Okay, let's go ahead. So for this question, what will be happening? Suppose we have the following neural network. What would the output of the network be if we give it the input x equals 0, 1? So again, we have very clearly 0 and 1 are the values. So this is the first value of the input. This is the second value. We use ReLU activation function gx is equal to max of 0x. So that means over here at each layer we use generally the activation function. So we are going to use gx over here, and we need to tell what is the value of like finally what we are getting. Oh, there is nothing over here. What we need to get, what is the output. So what is going to happen? Cool. Let's just solve this. So if I just talk about this, what would be your V1? What will be your V1? Understand it is going to be G of, basically the output over here would be G of, G means your activation function, ReLU activation function, what you'll be getting over here. So the value you'll be getting over here is x1 into 1 plus x2 into -1 and then 1 into -0.5. These all has to be added. That means what x1, let me just write like this, into 1 plus x2 into -1 plus 1 into minus 0.5. So what do you get over here? G of what is x1? 0. So nothing about this. x2 is 1. Minus 1 you'll be getting. What you'll be getting from this one? It is minus 0.5. So it would be minus 1.5. And you'll be getting, because it's a ReLU function, you'll be getting a 0 over here. So you'll be having a 0 output over here. What about this one? V2. So for this one, again, you need to do the same thing. V2 would be G of x1 into minus 1. See, this one is coming, and this one. Plus x2 into 1 plus 1 into minus 0.5. What you'll be getting? Again, x1 is 0. This is 1. So this is 1 minus 0.5. 0.5. So G of 0.5 would be what? It's a positive number. So you'll be getting 0.5. So what you're having is 0.5 over here. Now what you'll be getting out of this? Again, see, on the final layer, we generally do not have the activation function. In the final layer, okay, we have some other kind of activation function, not the ReLU, because it depends upon the kind of work we are doing. So right now, I'm going by the assumption over here for this particular question and not having ReLU activation function. If we have, you know what to do. So let me just tell you what would be y value, what we'll be having. So again, 1 into 0, 1 into 0.5, 1 into minus 0.5, and then we need to add. Overall, what we'll be getting is 0 only. So I hope you could understand what is happening over here. Any problem, do let me know. Okay. Let's move on to the next question now. Suppose our input is two-dimensional sample points. So what we are having is, again, it's a very interesting question. Let me just write it up. So we have two inputs with 10 non-exclusive classes. So we are having 10 exclusive classes and we are solving a classification problem. So it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. These are the outputs, number of outputs we are going to have. Okay, because I need to get some probability for each of the class, or basically some idea that, okay, that for the input, what is going to be my class. So non-exclusive classes, a point can belong to more than one class. Okay. Non-exclusive. Okay. To train a classifier, we build a fully connected neural network with bias terms that has a single hidden layer of 20 units. So that means we have a hidden layer also, which is going to be like consisting of 20 nodes, 20 units. So it's like this. So we have 20 hidden nodes. Okay, and an output layer of 10 units, each one for each class. So what we'll be having is we have 10 nodes over here and then 10 nodes over here, 2 over here for input, each of the input we are having. And it would be a fully connected layer kind of a thing, something like this, something like this, and something would be happening over here similarly, like this connected to all, again, this connected to all, and something like this. So this is something we are going to have. Now, how shall we be solving this? Like which statement holds true over here? Which that is something we need to understand over here, and it's interesting to see what is going to be the answer. For the output, can you use the sigmoid? See, sigmoid would still be able to tell you the probability for each of the class, but it would be independent of each other. That means whatever you will be getting for one particular class, you might get 0.8 and you might get 0.8 for the other class as well. So that means same probability you can get for the two classes, and which would not really add up to get 1. But for a classification problem, something like overall multi-class classification, what do we want is generally whatever probability returns you're giving the probability sum of all those values should be 1, because it has to be telling me that, okay, what are the chances of neural network saying that it belongs to this particular class, this. And overall, we have only this particular choice only. So in that case, you have to divide anyhow. 20% chance is this, 30% is this, 10% is this, and something like this. So you have to do something like that. So your sigmoid would still be able to do, but the problem would be, as I mentioned, problem would be that it would be independent from each other, which we generally do not want. Okay, we need to use our softmax activation function over here in that case, which works like something like this: e to the power z upon sigma of e to the power all these is whatever we had. Okay, let's suppose I had just it for out of one particular output layer, like one particular output node over here. So in that case, I'm saying z1 over here. So it would be e to the power minus z1, whatever is the output, and summation of whatever values you were getting out of all. Then in that case, you'll be considering all those summation of e to the power, and then you get what is the probability that it belongs to this particular class. And that's how you generally use softmax activation function. So definitely, our softmax activation function is more appropriate than just a sigmoid activation function. Okay, this network will have how many parameters? So if I just talk about this, we have, see over here, we generally do not, we have some set of weights over here. Now, what is going to be that? So we had 20 nodes over here, 10 over here, and we are considering bias every time. Again, we have 20 nodes over here, 2 input nodes over here. Again, we need to consider bias. So let me say if this is W1, if this is W2, in that case, what is the number of parameter in W1? So that is going to be 2 into how many nodes we have? 20 plus for all the bias for each of the node in the hidden layer. We are going to have this, which is going to be around 40, 60. Okay, what about W2? Again, same thing. So it would be 20 into 10 plus 10. So it would be 210. 210 plus 60, it's going to be 270 trainable parameters. I hope you could get this. Okay. Now, what's next we are having is the C option. Let's see. For the hidden units, a ReLU activation are more appropriate than linear activation function. Do you agree? The answer is yes. We do not consider the linear activation function. Linear means we are not having any kind of a, what should I say? Any kind of function on top of whatever we were getting as an output from previous layer. Why ReLU is important for us? See, ReLU actually helps in solving a number of problems for us because we want to understand non-linear, what should I say, or complex pattern we need to find out within our data set. If we just have linear activation functions, then if you put any number of layers side by side, what you'll be getting as an output would be simply a kind of linear regression thing, because it will be just weight multiplication every time, like W1 into W2 into W3, and whatever was the input over here, whatever you are getting over here, that would be just a linear combination of what you had initially. So that means it would be just a linear function, but you need to introduce non-linearity to identify complex things. So that's how you need to bring up some non-linear activation functions, and ReLU is just one of those. So ACD is the correct option over here. I hope you could get this. Now we will move on to the next question. You are given a multi-layer perceptron, an MLP, with one hidden layer consisting of 8 perceptrons. So it's just that you're talking about a hidden layer where you have 8 nodes, something like this, and a single output neuron you're having. Okay, so you're having something like this. Over here you're having the output. Okay, so it would be connected to all of this. Okay, something like this. Now, which of the following statement is true about the function capacity of the network? See, perceptron would be outputting you 0 or 1 depending upon the input. So that means this would be 0 or 1, this would be 0 or 1, and so on to everyone. So it is like I'm having 8 different inputs. All of them are binary in nature. Now, what can be my final output? How to do this thing? How shall we be solving this? So just think about this. Number of functions I can implement using this. Very simple idea. I'm having 8 inputs over here. 8 inputs. So what can be the number of possible outputs we can have? A total number of Boolean function, if I want to talk about this over here, what is going to be that number of Boolean functions over here? Can you think about this? Anyone? Okay. So it's going to be something like this. If you have studied something like digital logic or not, I don't know. So let me say x1, x2, x3. So you have these 3 inputs you're having. So in that case, just giving you the context over here. So what is the possible number of combination you can create out of this? So it is 2 to the power 3. 8 combinations are possible. That means 8 rows. Now, the function you'll be talking about would be that, okay, what is the total number of functions you can create from this? That would be coming out of that, okay, what are the rows I'll be picking up to give my final function value? It can be something like, okay, 8 I know. So I can choose 8C1. That means just one row and give me I'll give just one value as a final output. Or I can choose any 2 from this. I can choose any 3 and something like this. I'm just giving you a context to solve this problem up to 8C8. So what does it return? Like what I'll be getting finally over here. If you understand that. So in that case, what you'll be getting is 2 to the power 8 over here. I hope you understand. Okay. The way I have told you this one. So in a similar manner, if you really want to understand what is going to be happening over here is that, okay, I'm giving 0, 1 over here, 0, 1, 0, 1, 0, 1, 0, 1. So what is the total possible combinations I can create from this is 2 to the power 8 combinations can be created. Combinations can be created over here. So it's like 256. Okay. Now that many combinations can be created over here. Now if I talk about what can be this function about. So in that function, I can create a function which will be giving me an output based on any of these 256 outputs combination. So how many combination of these 256 can be done? So it's similar to this one, like the way I did when I had just 8 outputs over here, 8C1, 8C2, 8C3. So over here, what we need to do is on a similar line, like we are not having the correct options over here. It is going to be 256C1, 256C2, and something like this. Okay. So what is it going to be? 2 to the power 256, which is nothing but 2 to the power 2 to the power 8. That is the correct answer. So it should be this one, 2 to the power 2 to the power 8. So A would be correct answer if I say something like this. I hope you get it. So this was our 6th problem, and we have 14 more problems left. I hope you're tracking it. We have got some good number of questions over here. Amazing set of questions. Now, this is an easy problem we are having over here. Why is bias especially important in MLP with many layers? Why is bias important? So we understand that we will always be having some activation function. And for us, if I say G is an activation function, G would always be applied on W transpose X plus B, something like this. And W is my weight matrix, X is my input or from the previous layer or from the directly input. Now, B generally helps it in making this value from W transpose X a little higher or a little lower. Like it would decrease or increase this value. Now, the most common activation function, if we take an example, that is ReLU. ReLU actually gives me only positive number out of this. If the input was positive, it will give me that number. If it was negative, in that case, it would return 0. So you can see just from this context only, from the ReLU function itself only, that bias can help me give a proper output of the input nodes if I'm using bias properly. And if not, in that case, it would be a problematic situation. Okay. So what is going to be the final answer over here? Bias ensures each neuron has the flexibility to shift its activation threshold. So I hope you're getting. So activation function, like, because like going by the idea of just ReLU function over here only. So if I'm saying max of 0 comma x or 0 comma z, and z is calculated by this one, z equals w transpose x plus v. So in that case, you can see I can shift this z value itself and can make it positive or can keep it negative depending upon how much of b value I'm using, and then making it a little flexible to shift my threshold values. Okay, so that's how A is going to be definitely one of the correct option for us. Does bias guarantees convergence? The answer is no. Without bias, gradients cannot be computed. The answer is no. We can easily still calculate the gradients. Bias prevents vanishing gradients. Nothing like that. Nothing related over here with respect to the vanishing gradient problem. I hope you could understand. Okay, let's move on to the next problem. Okay, something related to the perceptron, and very simple, very easy question. Geometrically, what does a weight vector W in the perceptron algorithm represent with respect to the decision boundary W transpose x plus B equals 0? So if you understand it, if you understood the very fundamentals correctly, what is going to be the answer to this? W represents a vector, or yeah, it's a vector which is normal to your decision boundary given by the hyperplane, or basically normal to the hyperplane you give. So what is going to be the answer? It's going to be C. Very simple, very easy. Let's move on to the next one. What happens on non-separable data with classical perceptron, with classic perceptron? See, if the data is non-separable, we have a problem for the perceptron algorithm, because perceptron algorithm wants linearly separable data. If they are not separable, in that case, what would happen is every time I'll be having some misclassification, which will modify my weights, and I will never be getting perfect weights, which will lead to the convergence. So that means it would always keep on cycling through the updates only. It will never converge. So C. I hope you're getting. Okay, simple problem. Now this is interesting. What you need to calculate is binary cross entropy. Okay, do you know the formula? Because that is something which is being used for the classification problem. A number of times we use binary cross entropy loss as well. Okay, so in those cases, what is going to be like, how do we calculate that? Do you have the idea? So we generally have this formula which is given to you as a part of hint. You can just use this formula and you'll be able to get what is your binary cross entropy. Now, how do we use that? That is important. So we know, like, you must have gotten this, that we need to average it out. This is nothing but your kind of a cross entropy only. This is cross entropy for one row. Okay, if you just keep I equals 1, so in that case what you're telling is, for first row, what is going to be the cross entropy, binary cross entropy. Now overall binary cross entropy you will be finding out for each of the row over here, and you have around 5 rows. So you need to calculate and you need to average, and that would be your final binary cross entropy loss. Okay, now just telling you how to calculate. I would not be giving you the final answer. You can do that very easily using the calculator and all. Okay, so how to do that? So what you're having is yi ln p I plus 1 minus yi ln 1 minus pi. So I'm just calculating this part which is in the brackets, not the minus, because by the way, like, binary cross entropy loss would be just minus, but because we take it for everyone, that's why it had been separated out over here, minus. So let me just calculate binary cross entropy for the first one. So what will it be? So you can see over here. So the true label is y equals 1. The predicted probability is this one. What is the false one? That is 0. the false label, okay, is going to be this 0, and what is going to be predicted probability for that from this idea? It's going to be 0.1. I hope you can see this. Very easy. Okay. So if I just tell you how do we use it over here? So for this one, we had 1. We had ln. What is the probability value? 0.9 already. What do we have over here? See, this was already doing good, because if I had this consider it, if it was a perfect thing, 1 was the value. In that case, my loss would be 0 for this one. I hope you can see this. My loss would be entirely 0 for this one. Okay. Okay. So yeah, going further. So what would I be getting over here? It is 1 minus 1 over here, because the other what should I say? The other label I'm talking about is 1 minus 1, which is 0. This is what I'm talking about. ln 1 minus, what is the pi over here, which we had? 0.9. So I'm talking about 0.9. So what I'll be having is ln 0.9, negative of ln 0.9 as my binary cross entropy loss for the first row. And then you can calculate for all, and you can divide by 5 to get the overall binary cross entropy loss. Okay, I hope you could get this. Okay, now look at this 11th problem. The neural network we are having. So right now, so we have the binary inputs x1 and x2. What is the logical function it actually controls or output? So let's write it and understand. And it is nothing but a kind of a perceptron only we are having over here. What is going to be z, and then what is going to be my output? Okay, let me write this. So let me just write 0, 0, 0, 1, 1, 0, 1, 1. What is going to be z? So 0 into 15, 0 into 10, minus 20. What you'll be getting is over here, minus 20. Okay, now over here, 0 into 15, 1 into 10, plus minus 20. So that means you're getting 10 and minus 20. 10 minus 20 is minus 10. What you'll be getting over here? You'll be getting minus 5 over here. What you'll be getting over here? You'll be getting 5. 25, yeah. What is going to be the output? So you get an output if x is greater, sorry, if your output is greater than 0. Okay. So that means for this one, it would be 0, 0, 0, 1. So can you see, just observe x1, x2 and the output. What is the logical function we are implementing over here? Is it AND gate? Is it OR gate? Is it NAND gate? Or none of these? So it's a simple answer. We have an AND gate over here. This is working like a NAND gate. I hope you could understand. I hope you could get this. Easy question. Now something very, very simple, very intuitive. A perceptron is trained on a data set where all feature values xi are positive. So all the feature values are positive and all the true labels are also positive. That means we will be having always positive label plus 1. If the perceptron is consistently misclassifying points as minus 1. So that means I had all plus 1, but my perceptron is misclassifying every time and making it minus 1 every time. The learning algorithm will primarily attempt to adjust the weights and bias in which direction I shall adjust it. So the idea is, what shall I be getting? So just from this idea over here, I'm already saying x is always positive for me. I'm not knowing about W or B. And I hope you remember the way perceptron works is they just look at the sign of this. So that means there is definitely a problem with sign of W and B, because not necessarily B, it can be so like any combination of W and B. If it is positive, it was too much of negative problem. If it was negative, it was positive, but it was more negative, in that case again a problem. Okay, both are negative, problem. So what we need to do is I need to make this output positive so that the sign becomes positive and I return plus 1 as the label. So the problem is with these parameters W and B. So what do we need to do with that? Increase the magnitude. So do we need to increase the magnitude? So there are two things always associated with the variable. So one is the sign and one is magnitude. So for an example, -5 and -10. See, both are negative, but the magnitude of this one is higher than this. Magnitude means without sign, if you consider what is maximum. And if I just forget the magnitude, if I generally talk, in that case, I'll say this is higher than this. So that means I would like to increase -10 to -5 or -5 to +2, something like this. So we do not really wish to increase the magnitude, but the number itself, because increasing the magnitude, if something was -10 and I'm increasing the magnitude, it might become -20. That would not really help me. So I do not wish to increase the magnitude, but increase the weights and bias. So C is going to be the correct option over here. I hope you're getting. Question number 13, again a perceptron bias problem. So we have W equals this, bias equals 0.1, given and weight, given an input, learning rate is this one, true label is Y, calculate the new weight vector. So what is the, what is going to be the W? W would be W plus eta times of Y X. That's how it works. So what is initial W? 0.5, 0.5. And point to be noted, see, this only works for the misclassification. I'll get this, that what is the value. Okay, let's just use W transpose X, what we were getting. So plus B. So W transpose X. 0.5 into 1 would be 0.5. Minus 0.5 into 2 would be -1 plus B is 0.1. What do we get? We get something like -0.4. So we are really like getting a negative answer. So that means it will give me class label to be negative. And I want it to be positive. I want it to be positive. So that means I should increase the weight. Now how to do that? We already know. This is the update rule. Y is +1. Eta is 0.1 into 1 into what is X? 1, 2. Use it and then you'll get the answer. 0.5 plus 1 is 0.6. Minus 0.5 plus 0.2 is 0.5 minus 0.5 plus. So you'll get -3. Minus 0.3. This is the vector you're getting. So what is the answer? B is the answer. The updated weight. I hope you could get this. Which statement best describes the perceptron learning rule? So I just talked about this in the beginning as well. So what happens is, I hope you know that we talked about this idea, W equals W plus eta Yx. But there is again one more update rule which is similar to this and goes like this. What is the difference between these? See, if the one important point is we update only for misclassification. So it's like this. If the true label was 1 and I said it to be, let's suppose -1, in that case, I want to make it 1. So in that case, I want to make my W transpose X plus B more positive, or basically increase the value so that it becomes positive. So I need to add something to it. So it makes sense that Y is positive. Overall, I will be adding. If the true label was negative and I presented it to be positive, in that case, I would like to reduce the weights. So Y would be negative in that case and W would be reduced in that. Makes sense. This one is clear. What about this one? Again, same thing. If they are same, in that case, no update. Over here, if I go by this rule, if they're different, so that means, let's suppose if I'm saying Y was 1 and this was -1, I said. That means what we predicted was negative. So that means that is wrong. It has to be positive. We shall increase it. So what is happening is there is a minus, and what we are doing is 1 minus -1. So it would be twice of eta times X. So can you see? It is a kind of running just with a double pace only over here. And we can just adjust it by just adjusting for eta over here. Okay. Now, in a similar manner, if I say that what we predicted was again a misclassification, where we said plus 1 and it was actually a negative 1. So what would be happening in that case? Minus 1 minus 1. So what would be it? Minus 2. So that means actually it's minus 1. What we said was 1. We shall be decreasing the weights. So this is minus 2. It would be decreasing by minus 2 eta times. Something like this. So again, yeah, this also works fine. This is also one of the valid update rule we are having. So we have both. You need to just remember where do we use which one. Generally, you will find this one only. And when we talk about this one, whenever there is a mistake occurring, we generally do this. Okay. Okay. Now, if I just go by this idea, so we generally adjust for only when we have a mistake or misclassification. So if going by that idea, this is going to be the correct answer. Weights are adjusted by adding eta times of y minus y cap only when a mistake occurs. Okay. I hope it's clear. Now we have again a very good number of questions on SVM. Again, very important, very interesting set of problems on SVM. Read this and then okay, let me just show you what we have. We have some good set of problems. Yeah. Three problems which are geometrical. Okay. So you can just read through this and then we'll solve it. Consider a soft SVM formulation for following classification problem. So I hope you know from the soft SVM formulation, whenever my data points crosses what? Crosses the margin lines, in that case, my slack variable becomes non-zero. Okay. And if it is on the boundary or on their side only, in that case, it's 0. Other thing, if I talk about support vectors, are those which lie on the margin plus which are crossing the margin on the opposite side or just on the completely opposite side of the hyperplane as well. So what we need to find out is A represents the number of data points where slack variable value is 0. Okay. So we need to find out data points where slack variable value is 0, and B is going to be the number of support vectors we need to find out. Okay. So just think about this. It's a really interesting one. Okay. It's a really interesting problem. The soft SVM formulation problem over here. So if I just talk about this, what is going to happen over here? Slack variable, as I mentioned, once again, let me just tell you, the slack variable would be 0 for all those data points which are on the correct side of the decision boundary and on the margin or on the correct side of the margin. So that means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. 11 are those data points where my slack variable value would be 0. Why is it so? You need to understand why. See, I hope we have marked everyone. Not this one, because this was crossing our hyperplane itself. Why this one? Crossing hyperplane. Okay. Why not this one? Because this was again on the wrong side. So slack variable will not be 0 for this one. So what we are having is around 11 is going to be the number of data points which have a slack variable value 0. I hope you got this. Now, what about the other thing? That means how many data points would be there for which we are having like support vectors, like which data points would be working like our support vectors over here. Can you identify those? Just do it. Support vector, very easy problem. So if I just find out that, what I'll be having is this one is support vector. This one is support vector for sure. Okay. on the line, whichever we have, they are the support vectors. Which are on the opposite side of the boundary, definitely they are also. Whichever is having misclassification, that is also. So how many support vectors we are having? 3 plus 3, 6. 6 are the support vectors we are having. I hope you can understand this. If you have any doubt, please let me know. So what is going to be the final answer over here? 11 plus 6, that is 17 is going to be our answer over here. Interesting problem, helping you understand everything. Again, very interesting problem. This we formulated number of scenarios over here. And if you can answer this, you are already really good with respect to the understanding of SVM. So we are having a hard SVM formulation. Consider the following scenarios. Okay, let A be the number. Okay, so and these are the data points we are having. So just consider 2D space where we have these 4 data points belonging to the blue class, these 4 belonging to the red class, red or cross, blue or circles. Okay. Now I'm saying let A be the minimum number of data points that must be added to the data set such that all the points, including the newly added one, become support vectors. All the data points become the support vector. So for that, what I'm trying to say is it's something like this. And I'm talking the hard SVM. So in that case, I must be having something like this. Now for this to happen, how can I get this? Because right now, if I just think about this, without having any data point added, this is going to be kind of my decision boundary I'll be having. Okay. This is going to be my decision boundary and this is going to be my overall margin. If you can see this. Okay, this one. But I want this one to become my margin because I want all of these to become support vectors. So what shall be the number of data points I shall be adding? Point to be noted. Let me just, oh, we don't have a space over here. But I can solve it over here. Need not worry. Let me just mark it like this. For the first scenario. For the first scenario, what to do is A. Okay. I shall be having a data point, any data point of red color or red cross on this side, on this line, anything over here. Because if I add over here, I'll get something like this margin. I don't want that because in that case, every data point will not become support vector. To make them, I shall be getting something like this. And for that, I must be getting these shall be my perpendicular distances. So I must have a data point, red data point over here or something on this side or a data point belonging to the blue class or a circle, something over here. Anyone here or on the left hand side of red, anyone over here or on the right hand side of this. If I have any of these, I'll be having all these data points becoming support vectors. So the answer to this one is just 1. So A is 1. What about B? Let B be the minimum number of data points added that must be added to the data set such that the closest points from different class. So what are those? This one and this one. Right now, these are the closest one from different class become support vector. They were already support vectors. You can see over here. So we need not really add anything. If we have these data points only, in that case, this and this was already a support vector. So in that case, B value is 0. I hope you're getting. Now, next, what we are having is C. Let C be the minimum number of data points that must be added to the data set such that we get vertical decision boundary. So what I'm saying is, I'll just okay, I had this one and we had this one. Now what I'm saying is I want a vertical decision boundary. This cannot be like this can be over here, like it depends. Okay. So how can I get a vertical decision boundary? How shall I get something like this as a decision boundary? So for that, what needs to be done is something like this. if I add a data point of plus sign over here, or a blue sign, a blue circle over here, we are done. This one or this one, I'll get a vertical decision boundary in that case. So that means I just need one data point over here. So what is the value of A? 1, B 0, C 1. 1 plus 0 plus 1, that's 3. 3 is the answer. I hope you could get this. Interesting problem, good problem. The last complicated but still amazing problem we are having. Yeah. So, okay. So within this question, we'll be talking about both hard SVM and soft SVM formulation, both. Now, if I consider both, what is, so we are going to use some M2, M1 or O values. What is M1? M1 is telling me slope of decision boundary for linear soft margin. If I consider a soft margin, and within that I'm saying C is not too extreme, that is, it is not too hard, too large, or it is not too small as well. We're getting good number. So in that case, what shall be my margin or decision boundary look like? And if I draw the decision boundary, what should be the slope of that? So if you just look at this, if I consider, right now, if I just consider there is hard SVM also and soft for these two. So if I consider hard SVM, I know this point belongs to the same class, this. So in that case, this is going to be my decision boundary. I hope you can see this. So that means what I'll be having is y is equal to 2.5 is going to be my decision boundary. Okay. So that means what is the slope of this line? Can you see that? The slope is 0. So that means M2 value I'm already having. M2 is 0. Now, if I'm not having a hard SVM but a soft SVM, then in that case, can I increase the margin? Right now, the margin is this much. I hope you can see this. Can I increase it? Yes, by allowing some misclassification, because I'm saying I'm not increasing too much, I'm not decreasing, but I can allow some misclassification. That means just look at something like this. If I bring something like this would be misclassified. This would be misclassified. This would be misclassified, but still fine. But overall, you can see the distances of these are good enough. This is like much more. So in that case, these would be becoming my support vectors. Something like this would be happening in that case. I hope you can see. So if I consider a soft SVM formulation, what would be the slope of the new decision boundary? So you need to just find it out. So like we can just guess, like this is a simple guesstimate work over here with respect to like how does it draw further, because we do not really have all the data points plotted over here. That means the coordinate line is not entirely plotted, but we can still work out over here. Why so? If you just consider, see, whatever is the slope of this, that is the same slope of this. You can easily find out. You have the point 5, 3, 4, sorry, not 4. It would be 4.5. 4.5, this would be 3.5. This is 4, 4. I hope you can see this. Similarly, this is 2, 1. This is 1.5, 1.5. This is 1, 2. So you can see whatever is the slope of this, the same is the slope of this. And if you draw a new decision boundary over here, that would be also having the same slope over here. So that means you just need to calculate the slope, because that is what is being asked. You need not find out that what is here and there, like what exactly is the intercept. You need not find. Just tell me what is the slope. So can you find it out? Just calculate the slope from here or from here, and we are done. What is the slope of this? If I just subtract y2 minus y1 upon x2 minus x1, I'll get it. What is this? 2 minus y2 minus y1. It is 1.5 upon x2 minus x1. What is x2? So this was my first y2. So 1 minus 1.5. What is this? Minus 0.5. What is this? Minus 0.5. Sorry, this was plus. So what I'll be getting is -1 over here. I hope you can see this. I'm getting a -1 over here. So if you're getting -1, that means the slope is also going to be -1. So this value is this value is -1. This value is 1. Now, in the case of soft SVM, what is the number of outliers I'll be having? What would be the number of outliers I'll be having? Or like I shall have written misclassified point. So you can see 1 and 2, because these are the only data points which are on the wrong side. So these are the 2 points. So this is 2. Now what is the final answer? 1 minus -1 plus 2, making 4 is the final answer. I hope you could get this. Again, an interesting question to solve. 4 is the final correct answer over here. I hope you could understand. Very important problem. Okay. Now the second last problem. Which of the following are true for the support vector machine? Increasing the hyperparameter C tends to decrease the training error. So if I'm increasing the hyperparameter C, what was C for? C was for basically misclassification penalty. If I'm increasing the C, in that case, what I'm saying is no misclassification error should be there. If I'm increasing, I'm reducing the misclassification cases because I'm increasing the penalty. So that means it's true. If I'm increasing the C, tends to decrease the margin. Is it? Yes, because if I'm increasing, I am allowing a less misclassification. So in that case, the margins would actually narrow down. The hard SVM is a special case of soft margin. Yes. With hyperparameter C set to 0. No. Hard margin is a kind of a problem where I'm saying no misclassification. That means my penalty is too large. That means C shall be infinite in that case rather than 0. So the first part of the statement is true, but the second part is not true. So hence it's not true. Increasing the hyperparameter C tends to decrease the sensitivity. So if I'm increasing, am I decreasing or am I increasing? See, increasing C is increasing the penalty. If I'm increasing the penalty, I would actually react to every noise or any here and there in my data set. That means to the outliers. So that means this is false. So A and B are the correct options. Increasing the C tends to decrease. Yeah, it's false. Increasing the C would increase the outlier sensitivity. Last question we are having over here, and then we'll end it. Consider a binary classification problem in a two-dimensional instance space. You're given a linearly separable training set. You run the hard margin SVM algorithm and obtain a separating hyperplane below. Okay, we got this. Support vectors are circled. You can see that. What is the smallest number of data points that would have to be removed from the training set in order for the SVM solution to change? So what is the data point I shall change? So if you know, it most of the time depends upon it actually depends upon the support vectors. Not every support vector, if removed, changes the solution, but it is always one of the support vector which actually, if removed, can change the SVM solution. Okay, so what shall be happening within this case? What shall be the data point, or what shall be the number of data points? So just think about this. If I remove this, would my solution change? No. These two would actually still balance it out, keeping these distance like this. If I remove this, no. If I remove this, like removing this will work similar to if I am removing this. So nothing from this side. What about this? If I remove this, what would be happening in that case? Now have a look at this. If I just remove this, what we will try to have is, if I just remove this one. So over here, you can see this can go a little farther over here, and this can go a little over here. So that means it can tilt a little bit more, increasing my margin. So that means my solution would change if I remove this or even if I remove this one, my solution would change. So that means what is the minimum number? I can remove this or this. That means it's just one data point I need to remove, and then it can still change my SVM solution. So the answer to this one is going to be 1. I hope I'm clear. So I hope you enjoyed this session in which we solved around 20 problems from SVM, perceptron, and neural networks. Very interesting set of problems. I hope you have learned it. And trust me, like no, it's anticipated. I would say just anticipation. I can't say really 100%, but these questions are really important from examination point of view. Okay, you should definitely solve it to get an understanding how the questions can be asked within the GATE exam. Okay. So that was me. In the next class, I'll be bringing the next set of topics, which is from the unsupervised learning and one of the supervised algorithm called LDA. So in the next session, we'll be talking about those. And then on day after tomorrow, we'll be ending this up with the bias variance trade-off and the cross-validation error topic. Okay. Basically, your evaluation metrics and model selection parameters. So that was me, guys. Sachin, thank you for watching out this session. I hope you enjoyed this session. Please don't forget to share and give it thumbs up if you're really liking it. Bye bye. Take care. Thank you, guys. See you guys in the next session. Bye bye.